y'all, welcome to Miss Clarke's chemistry class. I am still here talking about solutions. I know, right? So much information about solutions. In this lesson specifically, we're going to talk about colligative properties. Colligative who? Colligative properties. Keep listening if you don't know what that means. This is a brand new vocab word in chemistry, so make sure you listen to this whole video. So go grab your notes, grab something to write with, periodic table, and a calculator. Just a little bit of math in this lesson. You know me, I love math. Okay, let's get started. Okay, so let's talk about what exactly a colligative property is. A colligative property depends on the ratio of particles of solute and solvent in a solution. I know, what does that mean, right? Okay, so basically, in easier terms, a colligative property is a property that changes when you add solute to a solution. I'm going to list 4 of them, even though I only talk about 2 of them. I know, I didn't really make that definition much more clear, but just bear with me. I think it will start to make sense in just a second. Okay, so the 4 main colligative properties. The first one is freezing point depression. For example, water freezes at 0 degrees Celsius. But we also know that when the temperature is going to get really low and it's been raining and we're all hoping for the streets to freeze over so we don't have to go to school, what do? We start sprinkling everything with salt. Now, you might think the salt is there to give you traction because it helps with the friction, and that's true. But really what happens is when the ice and the salt mix together, salt water, when you add salt to that water, it no longer freezes at 0 degrees Celsius. It freezes at a colder temperature. So when we lay out the salt on the ice, it causes it to melt because when the salt starts to create a solution with the water, it causes the freezing point to lower. That's what freezing point depression means. So if you have a pure substance like water and you add a solute to it, it changes its freezing point. It also changes its boiling point. This is why we add salt to water like when we're cooking noodles. Now, a lot of us just add salt to the water before we put our pasta in because that's what our mom does. That's what our grandmother has done. And we're just like, well, that's just what you do. It flavors the water. It makes things taste better. But that's not what happens at all. When we add the salt to the water, it causes it to boil at a hotter temperature. Pure water boils at 100 degrees Celsius. But when you add a solute to it, like salt, I know I keep using salt as my most common example, but when you do add salt to it, it causes the boiling point to elevate. So 2 of the main colligative properties that we're going to talk about in this lesson are going to be freezing point depression and boiling point elevation. Also, when you add a solute to a solvent to get a solution, it lowers the vapor pressure. And then the 4th one is the osmotic pressure. Now, I'm not going to spend any time, not hardly. I'm really not going to talk about vapor pressure lowering or osmotic pressure changes. Now, there's a mathematical equation because you can figure out exactly how much the freezing point is decreased or exactly how much the boiling point is increased. I'm sure there's math to figure out the difference between the vapor pressure lowering and the osmotic pressure change. That's just not something that I'm going to cover in this lesson. So here are the 2 formulas that we can use to figure out exactly the temperature change in the freezing point or the boiling point. This top formula here, we see this F, that means freezing. This is the formula we would use to calculate freezing point depression. Let me make sure that you understand what all of these variables mean. First, let me point out this triangle. Triangles mean change. So this triangle TF, this is going to be the change in the freezing point. And then this K sub F, that's called the molar freezing point constant. Molar freezing point constant. This number will always be given to you, just like all constants. And then we have little m. We just talked about what little m was in a previous lesson. If you don't know anything about molality, make sure and check that video out. But this little m, this is molality. I, this little italicized I, this is the Hoff factor. I'll come back to that in a second because we're like, what in the heck is a Hoff factor? And then if you notice the formula below, the exact formula, except we've got these B's for boiling point. So triangle T, this is going to be the change in the boiling point. This is going to be the molar boiling point constant. molality, Van't Hoff factor. Do I need to write those down? I kind of don't think so. Okay, let's practice using those formulas. Oh, but before we do that, we've got to talk about what a Van't Hoff factor is. I almost forgot. Okay, so a Van't Hoff factor is the number of particles after dissolving. So remember, in the first lesson of this series, in the solutions lesson, I discussed into which compounds dissociate and how they dissociate. So that all of that's coming back into play with this lesson here. Okay, so a Van't Hoff factor is just going to be a number. The Van't Hoff factor would be a 1 for all covalent molecules, because remember, covalent molecules do not dissociate. So if we were to dissolve a covalent molecule into a solvent, it's not going to dissociate, so it's still only going to have one particle. It's going to stay together. If we were looking at sodium chloride, that is an ionic compound. Now remember, for something to be considered an ionic compound, it has to be made out of a metal and a nonmetal. Sodium is our metal, chlorine is our nonmetal. That's how we know it's an ionic compound. We have 1 sodium, 1 chlorine. So when a formula unit of sodium chloride dissociates, it dissociates into 2 particles. So if we were talking about salt, then we would use 2 for the Van't Hoff factor. Calcium chloride, again, metal, nonmetal, ionic compound. Ionic compounds completely dissociate when you dissolve them in water. And since there's 1 calcium and 2 chlorines, they would completely dissociate into 3 particles. And then this one would be 4 particles because, again, ionic compounds completely dissociate. We've got 1 aluminum, 3 iodines. That would be 4 particles. Now let's look at this one. There's a polyatomic ion. We've got calcium, nitrate. This is an ionic compound, so it does dissociate. But if we remember way back, we learned that polyatomic ions are nonmetals bound together with a covalent bond. So nitrate in itself is not going to dissociate. Calcium nitrate is going to dissociate into calcium, and it's going to dissociate into 2 NO3 ions. Now let's try out these formulas. What is the new boiling point if 25 grams of NaCl is dissolved in 2 kilograms of water? And there's that molar boiling point constant. Okay, let me write the formula so we can remember what that looks like. The change in the boiling point equals the constant times the molality times the Van't Hoff factor. Let's go ahead and label these units. So Kb, I'm not going to label it because it's given right there. Molality, there's nothing in this problem that mentions the molality. So let's also write that formula. Remember molality, little m, and then that was going to be moles over kilograms. So we're going to have to solve that. So let's start there. And when we reread this problem, it doesn't talk about how many moles of sodium chloride is dissolved. It's talking about how many grams. So we're going to have to convert that. So we've got 25 grams of NaCl. Grams is on top, so I'm going to put grams on bottom. 1 mole goes on top because it's the mass of a mole, molar mass. Now we need to add up 1 Na and 1 Cl, the molar mass. Na is 22.99 plus chlorine, which is 35.453. I feel like I add this molar mass all the time. I should have it memorized, and I don't. We've got 58.443. So I'm going to put that in my calculator, 25 divided by 58.443 to get let me look at my sig figs, 2 sig figs, 0.43 moles. So I need to put this moles into this formula to get molality. It's going to be moles over kilograms. We've got 2 kilograms. So I'm just going to go ahead and set that up right here. 0.43 moles over 2 kilograms. Let's get that answer. And I'm getting 0.21 molal. Okay, now we're ready to finally use the actual formula we're here to talk about. The change in the boiling point equals, we've got the constant, that is 0.52. We have the molality, 0.21. Now we've got to think about that Van't Hoff factor. We're talking about sodium chloride. That is an ionic compound. So that would dissociate into 2 particles. So we're going to put a 2. Now we're just going to multiply. So I've got 0.52 times 0.21 times 2. In the change in the boiling point, keeping with 2 sig figs, is 0.22. Talking about temperature here, so that's degrees Celsius. But let's go back and look at what our question is really asking. It says, what is the new boiling point? This number here, this is the change in the boiling point. Okay, the boiling point of what? The boiling point of water. Well, the boiling point of water is normally 100 degrees Celsius. So if we take this 100 degrees Celsius, and this is boiling point elevation. When we add things to water, they boil at a higher temperature. So then we would need to add our 0.22. There's no reason to put that in the calculator. That would just be 100.22 degrees Celsius. That is our new boiling point. That was a lot of work, but the math isn't that difficult. Let's try another problem. What's the new freezing point if 42 grams of aluminum phosphate is dissolved in 3.5 kilograms of water? Okay, so let's write that formula again. The change in the freezing point equals the freezing point constant times the molality times the Van Hoff factor. And again, I didn't give us moles. That would make things so much easier, huh? I'm giving us grams. I told you, moles is never going away. Okay, so let's start there. Let's convert that into moles because we know we're going to need that to find molality. Remember, molality, moles of solute divided by kilograms of solvent. Okay, so we've got 42 grams of AlPO4. Grams is on top, so grams is going to go on bottom. This is the molar mass, so that is the mass of 1 mole. Now let's add up the molar mass of aluminum phosphate. So I'm looking at my periodic table. Aluminum has a mass of 26.982. And then we've got phosphorus. Phosphorus's mass is 30.974. And then I've got 4 oxygens. So I'm going to put this in parentheses. 15.999 times 4 close parentheses equals. And I am getting a molar mass of 121.952. So let's put that in the calculator. 42 divided by 121.952. And so I am getting, let's check sig figs, 2 and 2, 0.34. That's moles. Again, I'm just going to keep building my problem here because we've got moles over kilograms. Our kilograms is 3.5. And so our molality is, so when I put that in the calculator, I am getting 0.098. Okay, that's our molality. Okay, so now we're ready to put that in our problem. We've got the change in the freezing point equals the freezing point constant, 1.86, multiplied by our molality, 0.098. Now let's look at that Van Hoff factor. Aluminum phosphate. Now let's remember, phosphate is a polyatomic ion. It will not dissociate. So aluminum phosphate is going to dissociate into aluminum and phosphate. So that is 1, 2 particles. So I'm going to put a 2 here as my Van Hoff factor. Let's put that in the calculator. 1.86 times 0.098 times 2. Our change in our freezing point is going to be 0.36. That's degrees Celsius. But again, I didn't ask what's the change in the temperature. I asked what's the new freezing point. Freezing point of water is 0 degrees Celsius. So we've got 0 degrees Celsius. That's where we're going to start. And now this is something that you just have to remember. When you add solute to a solvent, the freezing point gets colder. Boiling point gets hotter. Freezing point gets cooler. So what's cooler than 0 degrees Celsius? Well, we've got to subtract to figure that out. Minus 0.36, which is just negative 0.36 degrees Celsius. Let's try one more example. When 5 grams of a non-electrolyte is added to 25 grams of water, the new freezing point is negative 2.5. What is the molar mass of the unknown compound? That is quite a bit of a different question, isn't it? Let's first start with writing our formula. That always gets your thoughts straight. And we're talking about freezing. So we've got the change in the freezing point equals the constant times the molality times the Van Hoff factor. Let's see what we have. Okay, so 5 grams, that's our solute. And there's really no place in our formula to put the solute. So we're going to kind of skip over that for a second. And then it's added to 25 grams of water. That's our solute. And there's really no place to put a solute here. Now we do have the new freezing point is negative 2.5. That's the new freezing point. Well, remember the freezing point was originally at 0 degrees Celsius. So if the new freezing point is negative 2.5 Celsius, then that means the change in temperature is just 2.5 without the negative. That's the change. To go, because remember a while ago we did 0 minus our number, and that equaled our new temperature. Well, if our new temperature is the negative 0.25, and this started out with 0, then what must go here? Well, it was 2.5. The negative is already built in. I hope that makes sense, that it's just 2.5 and not negative 2.5. Okay, so I've got 2.5 there. Now this problem, I did not list the constant because we just had it on the problem before. That was 1.86. Now we cannot figure out the molality because we would need to be able to convert these grams into moles, and we can only do that with the molar mass, and that's what we're solving for. So we're solving for molality here. And then the Van't-Hoff factor. At first look at this problem, it looks like we don't have enough information because we don't know what the compound is, but they give us a clue: non-electrolyte. And again, if you go back to the vocabulary in the very first lesson of this series of solutions, on the solutions lesson, we learned that non-electrolytes are often covalent compounds. And if this is a non-electrolyte, that's our clue that this is a covalent molecule. The Van't-Hoff factor for all covalent molecules, no matter how small or big, is always 1 because they do not dissociate in water. So now we've got to solve for X. Now I'm going to ignore this one because it's going to do nothing to our math problem, and it makes us have one less number to worry about. We want X by itself. Right now it is being multiplied by 1.86, so we need to divide by 1.86, and X equals 2.5 divided by 1.86, and I am getting the molality to be 1.34, and since we only need 2 sig figs, I'm going to leave that at 1.3. Okay, so that's our molality. Let's label that molality. Okay, now let's remember our molality formula. Molality was moles of solute over kilograms of solvent. Okay, so we have our molality. I'm going to put that in the molality spot, 1.3, equals moles of solute. We don't know that, but we do know kilograms of solvent. Well, we don't know kilograms of solvent. We have grams of solvent. So if we have 25 grams, remember there's 1,000 grams in a kilogram. That's 3 zeros. So we're going to move our decimal 1, 2, 3 spaces. That's going to give us 0.025. So 0.025. Now we need to solve for X. Right now, X is being divided by 0.025, so we need to multiply it to get it on the other side. So X equals 0.025 times 1.3, and that gives me 0.033 moles. So if we were going to convert our 5 grams into moles, we would put our molar mass right here. We don't know what that is, but we do know that's equal to 1 mole. And we also know that when we end up this problem, we're going to get 0.033 moles. So we have our problem set up. This is how we would normally convert our moles, but we don't know what this is. So let's rewrite that problem. 5 divided by what equals 0.032. This is the math problem I want to work. Now this is, since X is on bottom, this requires a little bit more algebra, and we can do the algebra, but again, I think these problems are easier if you set them up like a proportion. So 5 times 1 divided by 0.033, and that gives us, and so X equals, I'm getting 151.51. This last problem, that was pretty complex. I wanted to throw something out there complex for those of us that are ready. If you weren't ready for this problem and you were like, what the heck are you doing? I followed the first 2 examples. This one blew me out of the water a little bit. Don't worry about that. This is a pretty high-level question. Chances are you probably won't even see anything like this. Who knew colligative properties were so important? You don't think colligative properties are important? You don't like ice cream? If it wasn't for colligative properties, we wouldn't have ice cream. Stay tuned. I still have a couple more lessons left in solutions. Well, until next time, bye y'all.